welcome to RLC 201S. Yes, so obviously writing a test next week. It's going to be at 12, I think 12 to 2, and it's going to cover the following section. Essentially, it's the first 6 chapters in quotations, and I have essentially the scope of the. So you get 2 DC circuit questions. Can you guys all hear me?
Yes, sir. You can hear.
Fantastic. Now, yeah, 2 DC circuit questions, one easy one more challenging. You've got energy and tariffs, your AC fundamentals, and your RLC circuit, basically, which we'll be covering today, or we essentially have covered part 1 on campus, and we'll just continue with the remaining content of RLC circuits. So, Mr. Smolders, could you please present those questions you've addressed to me on WhatsApp, so I can just engage with them on the online lecture, if you don't mind.
Morning, everyone. Just to confirm, I was going through some of the past papers and stuff. Are you going to be requiring us to work out a certain question using a particular theorem under the DC circuits?
Yeah, so he's asking, will there be a particular theorem requested to be asked? So fortunately for you is that, for instance, like the first question, right, like I did mention to you from day one, I'm just going to mark you for the answers. So I'm essentially going to say use any method. Like I'm going to say find the current going through that resistor. The other thing is for the next type of question, I'm in between this thing of you're going to have to use your theorems, obviously, to solve what you call it, any method as well. But the issue that I'm fearing that on how I'm going to actually mark you. But I do have 2 general approaches, obviously, which I know are, which you can possibly solve them. So in conclusion, basically, there's no particular method you have to know. I'd recommend knowing all of them, because some of them will be a lot quicker than others. However, there is no limitation on the method you have to use. So I don't know if that's clear, Tyrone, for the upcoming test.
Yes, sir. I was just getting a bit confused because, okay, going through Kirchhoff's and superposition, I'm following and stuff. But as I go further, I was getting just confused between the different methods and then like tripping myself up and getting the wrong answer. But if I could just use Kirchhoff's or superposition and maybe take a little bit longer to solve the question, but at least I know that my answer is correct.
Yeah, no, that's perfectly fine. I mean, we have the lectures recorded, Tyrone, of Thevenin and Norton. Let me just make sure, because we did have the lectures online. I highly recommend you go watch it, because I think it's explained well. It's really not that difficult. Just quickly as some kind of revision. I don't know if you've accessed the recordings before. By the way, I hope you did. At least try to access the recordings and go watch the lectures. But obviously, I know you had a unique circumstance as well, so you obviously don't want to be overloaded with stuff. But Thevenin is fairly easy. You just essentially opening the circuit. You're removing what Thevenin and Norton is for. Essentially, is if you want one particular resistor. So you basically remove the resistor and have this equivalent kind of circuit. So Thevenin essentially making you where the resistor was, making it an open circuit, and you basically have an equivalent series circuit. And with Norton, you basically short that particular branch so that you can remove certain resistors, and then you make a equivalent parallel circuit. So it's actually fairly easy. If you watch the lectures, go over watch the lectures as in just watch it, because certain things will make things easy. But it's like you said, if you want to just stick on superposition and Kirchhoff, that's extremely fine. I have, like I did mention to the start, I wanted to be divergent. So for the first question will be easy. I know I'll just mark the answer. However, for the theorem question, I'm still trying to figure out how am I going to actually mark that. You know what I mean? Like, but I'll figure it out basically once I have the scripts in front of me. But I mean, I obviously have the solutions to that particular question, so I know what's the best approaches to probably use anyway. But anyway, I hope that answers your questions, Tyrone. Just go watch the lecture. You should be alright. And I hope you guys are also using John Bird as well as the other textbook. So yeah, any other questions regarding the test? Sweet. I think for the final might be a bit specific, but I'm keeping it a bit open for now. So it's not really a big deal. But go watch the lectures, man, and you should be alright. Any other questions, gents? Lucivaldo? Nothing? Can we move on with the content?
Yes, sir, for sure. You can continue.
Okay, great. Let's move on. All right. So I'm assuming everyone was here when we on campus when we obviously did this lecture. Yes, we start on RLC circuits. We did one example, a series type example that's in a textbook. I think this is what we did, and I wanted us to do another one over here, which is in essentially your John Bird textbook, just as a recap. But before I get to that, I just want to have a quick, I guess, 10-minute talk on particularly on this part of the lecture. So I've recommended to students to get this Casio FX99ES Plus because we can work with complex numbers fairly easier compared to the other type calculators. So I don't know if everyone has got this. So what I'm quickly going to do online, I'm just going to run a small tutorial on how to actually use a calculator. So for the guys who's good at this, I mean, obviously you can just like watch and listen or just zone out, whatever. But I'm just quickly going to show the guys. I've actually explained why we can use complex numbers and all of that. So yeah, that lecture's kind of passed. But I just want to run a small tutorial to show you guys how important getting this Casio actually is, and not only for this semester but particularly next semester. I mean, I don't want to mention like solving quadratic equations and solving, you know, all that other type of equations. Nevertheless, what I'm going to do now, I'm actually going to, if you go to your textbook, just get my textbook as well out here. I don't know why I can't see it. Where are you? There we go. On page, is it page? Let's get what page that is. Just going to spend around 5-10 minutes just quickly showing this, and then we can focus on RLC circuits. Page 5.3. I'm just going to demonstrate to you how to actually use a calculator, just to show you guys how convenient that is, right? So I'm just going to share my calculator on screen now, and then yeah, I don't think I can actually zoom it up, but it's fine. You guys should be able to manage it. It'll just pop up now. Cool. So I think that's fairly decent. Let me just clear up everything to make sure it's all clear. Mode, mode, man. Shift clear all. Sweet. Okay. So again, this is a calculator. Like I said, this is the FXX. Why did I forget it now? Where's my calculator? Anyway. And I'm gonna show you how to basically solve using this calculator. So the first thing you want to do is go to mode, right? Go to number 2, which is complex, and this will put it in the in complex mode, right? So I'm just going to start with a basic complex number. So I'll basically say 8 plus. So what you want to do is keep the number in front, and then we have I over there. So it's going to be just you click on there and it will represent itself as I, right? So you always want to make sure that a number, the number is in front of the so-called, the imaginary part is that the number is in front of the I, or as the I represents J. Credit Vian for picking that up. I don't know why I never figured that out. So this is obviously recapping on the complex numbers. This is in the rectangular form, and sometimes we typically want to work in polar form, right? Because you will understand certainly why. So what you do, let me just redo this, plus 5i equal, is that you sometimes want to convert between polar and rectangular and polar form. So you go shift, you go to number 2, and you click number 3. So it's the R with that angle thing, and then with theta with this. You press 3, and you press equal, and it'll convert that that complex number in rectangular form into your polar form, right? Obviously, we've learned that this is actually the phasor, right? So we get the magnitude at a respective angle. So I've explained what all of this is. So I don't know if you guys have actually went over this. So just as a further exercise quickly, if you're doing, for example, 5.1, you're just gonna literally say 8 plus 5i plus 5 plus 4i, right? You click equal, boom, you should get the answer 13 plus 19i, or 9j, sorry, or 13 plus 9, or 19. You're going to convert that into the phasor form or the polar form. You go shift 2 complex 3 equal, boom, and you get it. Let's go back, just click answer. Hopefully the answer, okay, anyway, shift 2 3 and equal. Yeah, so, and I'm just pressing that button over there with the S to D, which I'm not sure what it represents, but it basically just gets you from a fraction form into like a normal decimal type number. Okay, so yeah, so that's 15.81 at an angle of 34.69. So before I proceed further, is everyone aware of this calculator? Has everyone been using this calculator? Sweet. Okay, there's the guys I expected. Yeah. Sweet. Also just recording for the guys who obviously working out now. So I don't know if everyone got the calculator. I don't know if it's worth getting. Does anyone want to say, is it worth getting? Maybe Mr. VT, you want to talk about that? Just for the guys online when they view the recording, who's played with it, who's used to it.
Yeah, definitely. It's worth it. You guys must
100%.
get this calculator.
Yeah, sure. Thanks for the VT. Okay, Mr. Asa, I think, you know, if you have it. Anyway, can you please show B? Sweet. So I'm going to show, oh, yeah, there you are. Cool. Yeah, so showing B, did you just go back? So how you do B now is, obviously now one number is already in polar form and one's in rectangular form. So you're going to go 8. And now there's an angle thing, shift that. So again, right? So 8, shift, you're pressing where the negative thing is, the negative in brackets. There we go. You go 30 degrees, and then you go minus. Oh, did I just lose that now? 8 shift. Why is it doing that? Okay. 8. Seems like it's, oh, maybe I should have brackets rather. Let me just see 8. So you're gonna want to put brackets around that number. Otherwise it's gonna like run away. So make sure you have brackets around the number 1, I, and then equal. Then you should get that. And if you want to obviously convert this into polar form again, shift 2, 3, 2. You should get the answer there. Mr. Smolders, does that answer your question? Smolders, are you good with that? Okay, well, yeah. So that's that one. Trying, cool. Guy Lwando, mornings. And I'll just do one more just to kind of end off this, just the small tutorial. You're gonna go 8, shift that, and you can obviously even divide numbers. I'm doing C, by the way, 11 plus. Make sure you have the number there, and then your J or I over there, and so equal, and you get that actual number there, 0.585, whatever, and just obviously you can just call it like that. So that's like a small tutorial, getting everyone just for the guys online watching, when they do watch it, that they are aware that they need to get this particular calculator. Yeah, cool. So we can actually move on. So any questions before we continue with? We're just solving problems now, essentially. Any questions? Oh, good stuff. Fantastic. Okay, cool. I'm assuming that's everyone. The Casemiro represents everyone's feelings. Okay, so just I kind of left that out in the previous slides, and I did put it in. I talked about how we represent something called an impedance, which is now the new resistance for AC circuit, and essentially it has the resistance plus the reactance. So this part over here, the X, and we've talked about what these X's are, and they are due to essentially having an inductor and a capacitor over here. And we present the resistance now as or the so-called total resistance in the DC circuit is called the impedance as Z, but Z is represented as a complex number. And we still apply Ohm's law of V equals I times Z. This is just another representation of it, of how we actually can find Z. It's obviously just, it's essentially, if you think about it, it's actually two vectors, because they both have a coupled angle to it. For instance, just to explain, remember that we discussed that in an inductor, the current lags the voltage, and the capacitor leads the current leads the voltage. Obviously, that means there's some kind of phase shift happening. And obviously, if you're looking at it, the resistance has no angle. There's no phase shift because that's in phase. If you're looking at this particular diagram, because that's in phase with the voltage. And obviously, depending on how on the vertical vector, on what is your total reactance, you're gonna have to obviously subtract and add. And what you essentially do is then take the vectorial sum, or just rather the complex sum of it, and then not the sum, rather it's rather finding the so-called, I'll just rather use a vector sum of them, then we can find Z. So what Z actually is like the resultant resistance, which is essentially the impedance, right? I know that makes sense to everyone, of an AC circuit. So I just thought that's worth mentioning. Then just the notations of when you deal with certain things. So when you have a resistance, it's just a real number. I don't know if that makes sense to me actually. I should have called it type. But when you represent it, you just represent it 20 plus J0. It's the real counterpart of the total imaginary number. And yes, so that's an example. We can just have 20. That'll be perfectly fine. It's J times 0 will be 0, and they're all in ohms. And we have inductive resistance. It'll be a plus J, right? So an example there, plus J17. If you have a capacitive reactance, sorry, not resistance, inductive reactance, it'll be negative J. So if you obviously have a few different capacitors. Good morning, Mr. Gito. Oh, nice. Thank you for joining. If you have some inductive and some capacitive reactants, you've got a few of them. Obviously, you have to add them up. You know that the plus J part will be the inductive part, and the negative J part will be the capacitance side, the reactants. Hence the XL minus X subscript L minus X subscript C. So we always know that we have to subtract capacitance, and we're assuming that the inductance is plus, right? When I did talk about why it's plus and all of that, I did mention a few other things. Anyway, so we've done the first example. I think what's important to note here, and I don't know why in the textbook it doesn't say that, but let me just fold that shape up, make it yellow, and you must always remember that the voltage is always taken as the reference. So therefore, it's always at an angle of 0, because we relate everything to the voltage essentially. Whether current will be lagging or leading. Just again, the civil which I mentioned, this cute thing of this gabbing idea of how. So I don't actually I'm not going to ask, but you must know that in a capacitor, the current is ahead of the voltage, you enter CIV, and then the VIL part would be that the voltage is ahead of the current for the inductor. Obviously, that means it's lagging the current is lagging, the voltage was behind, and then whereas in the capacitor, the current is leading. So that is just a cute way of knowing the difference. It's obviously very important when you actually look at the numbers, and this is just graphical representations of what that was, right? Yeah, and I just talked about some applications there, nevertheless. So we did this example, and we'll be doing another one. So I'll discuss that at a later stage. Cool. Yeah, I think, I don't know, the guys who just joined now, I just want to probably just recap. Okay, I'll get back to the test scope. We can do that at the end. So next example is going to be problem 16. That's in the text, your John Bird textbook. So I highly recommend you get that one. I'm assuming you've practiced all the ones in the electros textbook. And we're going to do this one next. And that's our plan now. We're going to do one series one, then we're going to get into parallel. Cool. So we're just going to, it's only a lot of talk now. It'll be a lot of solving. So get the textbooks out and we'll be solving. So this is in the John Bird textbook. So just make sure if you have the soft copy of it, obviously you can use it on your phone or your laptop. Make sure you get it. Cool. So just give me a moment. My whiteboard is just loading up.
Hello, sir.
Sorry guys, can you hear me? I think I was muted for some reason. I'm sure you guys can hear me now. Oh, sorry. Okay, cool. So I literally read out the question. I spent all the time reading out the question only to find that I was bloody muted. Yeah, anyway. So like I said, what I essentially said is what we have is that we have 3 loads over there. Z1 will be an 8 ohm load. Z2 is a 5 ohm load with 130 micro Henry inductor. And the third load would be a 10 ohm 0.25 microfarad capacitor. And what I asked the students, or what I actually asked you guys, like what formulas do you use to convert your Henrys and farads into ohms? You actually just want to work in ohms, right? Yes, and so obviously we have these 2 formulas to actually just get that correctly. So the first thing we do is obviously convert those in. So for the first one, it's going to be 2 pi times the frequency. It's given at 20 kilohertz. And I mentioned obviously that this is definitely an electronic application with that low voltage and that high frequency. 2 pi that times 130 times 10 to the negative 6. Okay, so someone can give me that answer. And then when you work out your capacitive reactance, it'll be 1 over 2 pi times 20 kilohertz times what is it now? 20 kilohertz times 0.25 microfarad. So that's times 10 to the negative 6. Sweet. Then we can actually get our inductive reactance and our capacitive reactance now. Okay, so I'll wait on that answer from you. Just quickly do that. Just have a look. 16.6336 ohms. Yep, that's right. 16.336 ohms. Then your capacitive reactance. Let's see what you get there. That's capacitive reactance. Uh, 31,831 ohms. That's definitely correct. Okay, so you typically get a mark for getting those first. Just 1 mark for getting your reactance. Just 3 marks for those. Anyway, so once we have that, I think we can tackle and find the total current. This is series circuit, right? So it's still based Ohm's laws and obviously the law of the series circuits. So the one way what you want to apply is Ohm's law, but it'll be your current, your AC current times your impedances, obviously your total. Your total current will just be the voltage divided by Z. So you notice the book will use something different, but obviously we all mature people here, and we've got modern approaches on how to solve it. So I'll just show you 2 possible ways of doing it. Well, it's the same thing essentially. So we keep always 40 volts at an angle of 0. This is an absolute must. Make sure you have that. And then you're just gonna add the resistors in series as is. So for the first resistance, it'll be 8 plus J0 or I, whatever, plus, let me just extend that line, plus 5 plus J. So remember, we've converted that coil into this reactance, 16.336. We can make another bracket over here. And then obviously the last one would have been 10 plus, oh sorry, not plus, it's negative because it's a capacitor. So it's minus J 8, 31,831. And this is what I mean. All you have to do now is chuck this in the calculator and you can get the total current. Cool. So I recommend you guys doing that quickly and give me the total current. So you notice the book will have its own approaches and different books, but obviously my approach is always golden. So yeah, that's just the reality of, you know, life here. Just want to get something right here. Is it? Tell me if you get the answer. Let's see. Let's check the chat. Could please repeat the bottom one, sir? You mean this line over here? You mean the IV over? Okay. So what I'm saying is that this is still a series circuit. So obviously now for series circuit, you can add up all the resistance, like, you know, R1 plus R2 plus R3, exactly the same with this. I just said Z1, Z2, Z3. And obviously we know that the current's the same in all three impedances. So what I'm saying is that when you find the voltage, so the way you want to do it is keep your voltage as is, but make sure it's always referenced at 0. So this is a must, right? And then what we're doing is adding each individual impedance or each individual resistor, if you want to think about. So this is Z1, that is Z2, if you look at that particular problem, and this over here is Z3. You see there. So 5 plus, we've converted that 130 microhenry into 16.336 ohms. That's one load, and that's another load. Just tell me if you got that, if you understood what I meant. Okay, let's see. Why Z3 must be subtracted? Because it's a capacitor. That is what I was referring to before. Inductor, it's plus, and a capacitor is negative. Oh, maybe you joined late. Oh, it's Mr. Garcia, sorry. Okay, does it make sense? I think it does make sense. Yeah, and I'll come back to that just now. Show you why. Okay. So I'm still waiting on the answer. Yeah, here we go. The motors, are you following me? Okay, the current is 1 point here. That looks fantastic. Students, are you all able to do this? It is super important. It goes without saying here. And what's always important to make sure it's trying my best. Okay. I like the way you put the angle there actually. 33.967. So it's very important, 33.967. It's very important to represent it's a plus or negative, because this tells you that whether the current is leading or lagging. But smolders, yes.
So when you give your answer, how do you know when to leave it as is or when to convert it to polar form? Or must it
Typically,
always
like
be-
I always say, always convert it into polar form. That's like just the general thing. At the end, yeah. But you can keep it as both. It doesn't really matter to me. It's just easier. The thing is, the reason why I recommend polar form, because when you start doing power factor, you actually can find the power factor using this number over here. The power factor actually is the current's angle over here. So if you say cos of this thing, you actually get the power factor. So typically work in polar form, but if you have it in rectangular form, I don't mark you since you're wrong. I hope I answered the question there. But just that if you have the calculator, shouldn't even, work in polar. Yeah. I don't know if you had a question. Polar form, final answer. Yeah. I don't know if you want to say anything. Anyway, cool. So that's done. So that's a total current. That is quite easy. It's exactly the same idea of thinking with circuits. The phase angle, we obviously got it. The phase angle is plus 33.967. That means it's leading the voltage by that much. Obviously, from this, we can conclude it's a more capacitive circuit compared to a, it's a more capacitive circuit, so I'll say leading current. And obviously, we can actually see that over here because XC is greater than XL. So that's how we know it's a capacitive, it's acting more on a capacitive thing, for instance. That is important for whatever reason. Well, not yet. So the next part is obviously, typically the request is to work out the voltage drop across each impedance, right? So obviously we know in a series circuit, the total voltage drop is V1 plus V2 plus V3. It will follow the same rules. It's not constant. It's not constant. You can change depending on the reactance. If you change the frequency, it can change. Mr. Antonio Kitombo. So for your voltage, it's essentially the sum of the voltages. And let's start to sum up the voltages here. So obviously this will obviously be in polar form or some vectors or whatever, or phases rather. So for the first one, so voltage drop across the first load will be I1, I times Z1. So obviously the total current, it's the same current flowing through this whole circuit over there. It'll be I1 times Z1, which obviously will be 1.442 and plus 33.967. Again, I'll just literally type this in my calculator and boom, we sort it out. So it's 8 plus J0. That'll be V1. So you guys can get that for me. For V2, we take the same current, 1.442, 33.967. And we times by the second load, and the second load was represented by that whole thing. And that's going to be 5 plus, what's it? 5 plus J 16,336. So I hope you guys are following me here. So let's get V1 and V2 in the meantime. So the whole load is, just quickly showing you, it's a full resistor in AC, which is called an impedance, must have a resistor typically and some kind of inductor. Obviously, it's not that it must have, but that's how you know it's one. Obviously, they're kind of showing that to you. So I hope that's clear to everyone. So can you just quickly find V1 for me and V2? Let's see. For the first one, we have 11 point. Fantastic, Mr. Casimiro. I think this guy has a bright future. 11,536 at the same angle. That should be right. 11,536 at 33,969. That's the first voltage. The second one. Got to be the second one. So Duplessis, you awfully quiet. Are you following? Okay. See. Okay, nice. Okay. Second voltage drop over that, the load. Make sure you do this yourself. Okay, where was I now? 24.635, that's definitely correct. 24.635. You see the angle is not constant, the angle is changing. The only thing that stays constant is that the reference voltage. It's 106.949. Make sure you get that. And obviously V3 would obviously be the load. It'll be across that over there. So the 10 ohm or the 10 minus J. So capacitive, always remember it's negative. So this will be 1.442 angle 33,969 times 10 minus J 31.831. Okay, let's see what we get over there. That'll be the next current. Somebody on the next current. Just busy with something here. Okay, that should be 48.112 at minus. So you can actually, that's a lagging, not the voltage there. Its difference is 48.112, and an angle of minus 38 point minus 38.592. Okay, cool. So to make sure your answer is correct, if you add up the voltages, so V1 plus V2 and V3, it should equal to your 1440 at 0 degrees. I'm not sure what that is in, or it's like around. So just add the individual currents up and you should get the answer 40 degrees or 39.99 at. Just check what you get. It should be approximately this, obviously, because obviously we've rounded off and things like that. So just add up your voltages and you should get an answer close to that. What do you guys get? Yeah, 39.99. Yeah, fantastic. There we go. Is there any questions for this, guys? Let's open it up. You need to know this for your upcoming tests. I don't wanna make sure everyone gets it. So any part that I've left you. Just wait. Okay. Yeah, with a little more practice. Yeah, okay. Yeah, that's fine. Practice, obviously, yeah. It's a lot of examples to actually do in John Bird. You could easily get easily get that right. Okay, cool. Please explain what you wrote there about leading current and capacitors greater than inductance. Okay. So what I'm saying is, Mr. Duplessis, is that obviously we had to find the current and we had to find the so-called phase angle. But obviously, if you do this in polar form, you find it one time. You'll see in the book they have funny ways of doing the same thing, right? So what I'm saying is that if you have a positive phase angle over here, it tells you that the circuit itself is capacitive in nature, right? And what it means is that you notice that you have a higher capacitive reactance when you compare that to your inductive reactance. And that's basically what I just meant over there. And you will obviously this will result in a leading current. Like for instance, this might not be desired, for instance, to have a leading power factor, because if you're dealing with your for instance your alternators, your power factor essentially affects your voltage regulation. So you might have a positive regulation, so you might find it, or maybe a negative. You might find it that maybe like there'll be negative current, so to say. So that's why it's important to kind of know. And sometimes undesirable. Sometimes it is desirable because to have a capacitive circuit, maybe we're correcting power factors, for instance. So taking from you have a very poor power factor and you kind of time to correct it. So that's why that's just kind of important. But that's basically all. I hope I answered the question there. All right. So I hope we all are content with what is. I hope there's no questions here. Any questions, guys? Can I move on? Okay. So I think are we all good? Let's move on. Hey. Okay, great. So I recommend practicing more of those guys. I'm just gonna get back to this. Right, so we touched on series circuits. And like I said, if you want more practice, obviously you can do one in your textbook. And obviously this is coming in the test, so make sure you're able to do it. Exercise 6 will have around 2 series circuits, I think. And yeah, so, and obviously John Burr has quite a few of them. And you should be able to solve. So back to this again, I just kind of tidied this up. Looking at this, again, where the plus comes from is essentially that angle over there. So that plus 90 degrees, that's in phasor form. I have the same numbers in phasor form. And then the capacitive reactance is always negative J, whatever it is, ohms, and then that is negative 90. So obviously that feels a bit not very intuitive because one is leading and one is lagging. But nevertheless, those are the representation of how it must look like. Okay, cool. So we did that one, we did this one, and this is also a summarized setup of this. I don't know how useful this is. I just pasted it here. So depending on what elements we have, we can kind of predict what the phase angle is. But that's not in any particular importance. Yeah, I mean, you can just have a look at that. All right, so moving on to your parallel circuit, right? So for your parallel circuit, it's essentially the same, not the same, but it's the same as your normal DC stuff, where you have your voltage, and your voltage is the same across all three branches. And what they're illustrating, obviously, that the current splits, the total current supplied by the so-called alternator is split into three counterparts. So if you look at the first one, is that IR there, it's voltage divided by the resistance. The second part, to find the second current through the inductor is that the voltage divided by R2 plus JXL, which is obviously the plus is for the inductor, and then obviously the third branch we're going to have R3 minus, this is a capacitor, minus JXC. And then they do talk about hint when XL is divided into 3 into V, there has to be a lagging current associated with XL, blah blah blah. I'm not really particularly want to talk about all those things, but the idea is that the total current is a complex sum of all three. So I can't say complex sum actually, like vectorial sum. This was not supposed to be there, so my apologies. This was supposed to be at the end of the slide, and I'm not sure what version the book you have. I'm assuming you have the same version as mine, but there's more practice for series circuits over there on that chapter. So just let me just make sure. So you guys all have the textbook, right? Just that they have more practice. Just quickly say docs. I've shared this obviously. Make sure you check that textbook out. Chapter 29. Let me just see what's the same. No, yours is chapter 17, it seems. So 17 and 18. Yeah, I don't know the two different books I've shared here. So this is kind of null and void. I've got two different versions of this book. Yeah, anyway, so have a look at chapter 17 and 18. So I have to change this up here. So 17 and 18 instead of 20 and 28. All right, so let's do a parallel circuit. And this will be our first example. So this is example in your actual textbook. And that should be on page. So we're just going to have a small break after this one, and then we'll do some more examples and try to engage in more questions and stuff. I want to see if you guys are able to. Yeah, anyway. So let's just see. Yeah, okay, it's page 66, and let's see if we can actually solve this guy. So I'm just gonna get him on the whiteboard, and then we can move. Okay, new, cool, right. But I mean, essentially, if you've done all the stuff in the Electro 2 textbook, you should be more than sorted out there. I think the concepts are fairly easy to grasp. But yeah, okay, so just going to share the whiteboard and then just solve this one. And this is like the last content of the day, basically. Yeah. Cool. So we have this parallel circuit, and fortunately, in this case, they've given us, have they given us everything? Oh, let me quickly see. Oh, not actually. I'm just actually the complete form. So we have a parallel circuit powered by 110, 60, 110 volts, 60 hertz, American type system here. You've got 19 non-reactive load, which is parallel with a 10 ohm inductor, having an inductor rated J15. Then we have a third leg, which consists of a 18 9 microfarad, just not written properly here, 18 microfarad capacitor with an internal resistance of 8, right? Obviously they've worked it out. So the first step actually here was just to work out all your reactances. So that would have been XC over 1 over 2 pi FC, and that's going to be 1 over 2 pi times the frequency, which is 60, times the actual, oh, I think my laptop froze here. Okay, just give me a moment to just enter and exit again. All right, I'm back. I think my laptop had a bit too much. Just reverting back to the whiteboard. Can you guys all hear me? Just see is recording. Can you guys hear me? So we are just getting the capacitive reactance of that particular resistor over there, right? Am I audible? So this would be 30. Oh, so it's 89. Okay. This will be 29. 29,8. Okay. So your first step is typically to obviously convert your inductive reactance to capacitive reactances. Okay. Sweet. Okay, so once that is done, it's fairly simple. They want us to obviously work out all the currents. So fortunately for you, you don't have to draw any phasor diagrams or vector diagrams. It's not what I'm looking for. It's not a particularly useful thing to do, I think. So let's just quickly work out each current. So for I1, it'll be fairly simple. Like you said, we know that the voltage parallel circuit. Sorry. Parallel circuit. Therefore, voltage is the same. And just quickly get this right. So for the first current, it's very easy to be a voltage divided by your impedance 1. And obviously our voltage is 110, and we always keep this at 0 degrees, and Z1 is simply 19 plus J0. We can get that answer. For your second branch I2, that will be voltage over Z2, and it's just going to be 110, the angle of 0 divided by 10 plus J15. Now remember, that's already converted to inductive reactance. We can get that. And then I3 will obviously just be 110 divided by that. That's going to be 8 minus, because the capacitor, J29.8 equal. All right. So if you do the first one, let's see what you get. You should get an angle, a current of 5,7895 at 0 degrees. If you do the second one, you should get 6,1017 at minus 56.31. You can see it's inductive because we have a negative current over there, and we're expecting a leading current over here. So it's 110 divided by that, and you should get the answer of 3,5646 plus 74.97. So as you can see, we split through inductive, we get a negative current and we get a positive. So obviously they want a total current, and that's fairly easy. All we got to do is add up all the individual ones here. So we just have those lines to demonstrate it's a phasor quantity or vector quantity. So I total will be I1 plus I2 plus I3. You don't have to really write it as a vector quantity. I know what it is. And yeah, so just if you add the total currents up, what you get? what you guys get for the current. Obviously, gotta just the reason why I'm letting you doing so you just get used to your calculator. Are you guys still following? Oh, sweet. Okay, 10.23, 10.231. Thank you very much at minus 9.19 degrees. Okay, so that's our total current. It's a lagging current. And if you are interested in the phasor diagram, a phasor diagram is just basically a vector diagram, right? Phasor equals vector. You just call it different things in different thing. And what you just essentially have here is your current. So I1 will be at 0 degrees. We can think of balancing and all of this. A lot of the stuff is all the same. So that's I1. That's at 0 degrees. That's I2 is at minus 56. So that's around there somewhere. And what I3 is, it's plus 74. So obviously that is lingering somewhere over there. And what we're basically doing, because current has magnitude and direction, we basically find the resultant, which is in essence the vector, and that's at minus 9. So the resultant current will be I, that'll be I total. That's what your phasor diagram basically is. So as I say, it's not really a big deal. Is that clear to everyone? It's the same as forces, basically, if you think about it. So who knew current had a magnitude and direction? Welcome to S3. So clear to everyone? Nice. Okay. So let's have a break. Like I said, we're probably going to solve around 2 more circuits, or maybe I'll see depending. I'm gonna leave one on the board for you to solve, and then during the break, and then we can come back. So exercise 651. No problem. I can do that one. However, be cautious that it's going to take time. I can do 651, no problems. So you can do this one now in the break. And then I'll quickly go over this one. What I wanted to show you, there are what happens if you have something like this, and what happens if you have something like that. You should also be able to solve things like this, right? So yeah, but Jared wants 651 done, so you're gonna have to sacrifice one of them. 65 is not that obvious. Don't need to do it. Do we add the two capacitors? Yeah, the thing is, you can first find the reactances basically, and then just add them up here. You add the reactances, not the capacitors, because capacitors in series they like parallel resistors. Add capacitive reactance. Seems daunting, but it's not. So you can try it out and see. So convert everything to reactances and then just basically add them up, if that makes sense. And then you should be able to get it. I mean, we can do it, it's no problem really. Okay guys, so let's have I'm gonna give it 15 minutes. And come back at 10 past 11, and we're probably gonna do, like I said, another example. I'll just quickly run through this one. Make sure you do it yourself now in time. And then I'll probably do one more. Then I'll probably just go over the software just a bit. and yeah, then you're on your own basically. And yeah, so this one I'm gonna show you the one more example in the software, then we're done for RLC circuits. Not difficult, just engage with me via WhatsApp, whatever you need clarity on. Okay, so I'll see you at 10 past 11. So say tea break till. And sorry, 11. Okay, see you students. Stop sharing here.